This project was performed in partnership with Autocam Medical, located in Kentwood, Michigan. The team that worked on this project consisted of Timothy Gale, Zachary Visser, Dominic Fiorini, Alden Mallory, Aaron DeBoer, and Tyler Boovey. The faculty advisors were Dr. Blake Ashby, Dr. Ryan Krause, and our sponsor contacts were Christopher Colleen and Neil DeTurk. The project involves subcomponents of a cataract removal device. This figure shows all the components of the handpiece device, and the two main components outlined are the horn and the bolt. The horn is on the left and the bolt on the right. These are threaded and torqued together, and the plug, number 38, gets welded to the bolt. These components are currently assembled by hand. The assembly process involves picking a horn and bolt from tray and threading them together. Once the parts are threaded to hand tight, the assembly is placed in an air chuck and fixed in place. A wrench adapter is placed over the hex on the bolt, and a breakaway torque wrench calibrated to 46 inch-pounds is used to apply the final torque. The plug mates with the bolt at the weld seam, and a tip is threaded into the horn to orient the part to customer spec. The assembly gets set into an alignment tool and is placed into the laser welder. The plug is welded onto the bolt, and the alignment tip is removed. After weld, the part must be untorqued for specification checks that include concentricity, weld quality, overall length, and cosmetic issues. The scope of the project began as a horn bolt plug assembly cell that integrated with a laser welder. We quickly realized that the timeline for the senior project didn't allow for this scope to be completed. The idea was to have the robot assemble the horn and bolt together, torque them to spec, load a plug onto the weld seam of the bolt, torque an alignment tip onto the horn, place the loose components into an alignment tool, and move the whole thing to a laser welder. The plug would be welded to the bolt, the alignment tip removed, the horn bolt plug removed from the alignment tool, and untorqued for specification checks. The scope was changed to assemble and torque the horn and bolt together and place in a pallet for the weld operation. Once the plug was welded on, the assembly is loaded back into the cell for untorquing. Room was made for integration to a laser welder, and the pallets could be removed for different assembly operations, most of which included press-fitting parts together. The table layout was designed with the robot on the edge of the table, with the capability to reach outside of the cell into the welder. Aluminum plates with threaded holes were chosen as the tabletop for easy pallet changeovers for the other assembly jobs. The PLC, electrical, and air lines allow for many inputs and outputs to be programmed if needed. The team decided to use a single arm robot to pick, place, thread, and torque the parts together to the required torque specification. Requirements of the project included a cycle time of 2.5 minutes or less, hold the customer torque specification plus or minus 2 inch-pounds, fit in a 6x6 workspace, assemble to at least 25 parts at a time, and be able to expand for future operations. These include integration with a laser welder and other part assemblies. A major part of the design process was finding the best solutions to satisfy each of the initial specifications. The first objective was to design and build a tabletop for the robot to assemble the components. A team worked with a company called Vention to design a table that would fit our needs and hold all of the components of the designed cell. The final design is a 5 foot by 3 foot tabletop with enough room to fit all of the pallets, robot, the servo station, and the HMI screen. It also has enough room for the electrical cabinet and wires underneath the tabletop, with room for storage or future expansions. The UR5E was a robot of choice due to Autocam's familiarity with the style and teach pendant format. It is locationally precise up to 0.03 millimeters or 2/1000 of an inch. It also has a 3 foot reach radius, which allows for expansion of the cell. The robot is placed near the edge of the table with the ability to reach outside into a laser welder. It is also collaborative, making it safe for operators to work around the robot when it's in use. Due to this feature, an open table design was implemented. The Vootek torque sensor was a late addition to the project. Although the robot can hold the torque spec, the precision was lower than desired. In a manufacturing environment, the torque reading should be accurate to 1/10 of the specified tolerance. The torque sensor achieves the necessary precision and can read torques up to 100 inch-pounds. Unfortunately, the sensor adds 3.5 inches to the robot's end of arm. It restricts the horizontal movement of the robot because the parts are picked from a vertical position. The rotational axis around certain joints are also restricted due to the cable attachment to the sensor. The servo is a universal rotary unit from Schunk. It was chosen to work with the 3-finger gripper, which required 3 electrical feed-through and 1 pneumatic pass-through. It can torque well over 100 inch-pounds and has a 10 Nm air brake. This device caused the most problems with the build of the cell. It had a long lead time and didn't arrive until the last month of the project. A hold was put on position points for the parts, table layout, electrical wiring, and programming. The software setup posed issues with communication to the PLC programming as well. The 3-finger gripper on the servo is used to clamp onto the horn and hold it in place for the torquing and untorquing processes. It was chosen because it could apply over 2,000 newtons of clamping force. A material called quintus, produced by Schunk, was used due to its high coefficient of friction with the titanium material of the horn. This ensures that the part doesn't slip when torquing. The 3-finger gripper is also mounted concentrically on the servo. The custom pallets were originally designed to fit closely together in a group of 4 for the horns and 2 for the bolts. The horn pallets each hold 60 parts, and the bolt pallets hold 120, for a total of 240 parts. There are 4 pallets used for the assembled parts that are the same as the horn pallets. Due to the addition of the torque sensor and the size of the servo station, the layout had to be changed multiple times in the build phase. This led to changes for the part picking and placing on the pallets. The underarm tooling is attached to a collaborative gripper on the last link of the robot. The collaborative gripper is used for the same reason as a collaborative robot. The gripper can sense when soft material, like a finger, is in the stroke of the gripper. It can grip with a force up to 240 newtons. The underarm tooling is composed of 2 aluminum pieces that mate together. These act as a 3-in-1 pick and place device. The tooling is used to pick and place a horn and bolt from pallets. It also has a stainless steel insert attached to fit on the hex of the bolt. The insert is used for the final threading and torquing of the components. The use of the 3-in-1 design was chosen because it allowed for one robot gripper to align concentrically with the servo. Several issues came from the robot gripper, the stainless steel insert, and the mating of the aluminum tooling. The robot gripper came with more movement within the stroke length than was anticipated. This called for a redesign of the insert for the torquing. The insert also could damage the hex on the bolt. The damage included rounding of the hex corners and slipping during the torque process. The damage was too great to be considered acceptable to the customer. Lastly, the aluminum tooling was changed for better grip on the horn and the bolt. The Human Machine Interface, or HMI, is an Allen Bradley PanelView Plus 7, which was chosen for its size and communication capabilities with the PLC. It is not too large, but allows for enough modifications and setup inside the cell. It communicates to the PLC using Ethernet. The HMI includes screens for the machine setup, manual operations like spinning the servo, a fault list, torque station readout screen, and an advanced setup for the torque station. There are buttons on the enclosure for emergency stop, power on, and cycle start. There's also a stack light indicator used to tell the operators what state the machine is in. The assembly cell uses a UR5E cobot to pick and place individual parts from input pallets into the servo torquing station. The lower part of the assembly components is called the horn. There are 4 pallets that house the horns on the table. The robot picks a horn from the pallets and places it into the servo station. The servo station clamps onto the horn for threading and torquing. Next, the robot picks a bolt and places it on top of the horn threads. The robot repositions to the insert on the underarm tooling to attach to the hex of the bolt. The servo spins backwards to ensure that there is no cross-threading. The servo then spins forwards to thread the bolt into the horn. The servo station is equipped with bearing sliders to account for the Z movement of the threading. Different speeds are used to ensure that the servo torques to spec. Once torqued, the assembled horn bolt is placed into a completed part pallet to be welded. In total, the robot cell can assemble up to 240 parts. After the parts are welded, the pallets are brought back to the input side of the cell for the untorquing process. For untorquing, the finished parts get picked by the robot and placed in the servo torquing station. Once the part is secure in the Quintus grippers, The robot moves to the hex of the bolt. The servo then spins in reverse to break the part free. Once loosened, the robot places the components to the completed pallet. It is essential that these two components are not separated after the untorquing process.